Okay, so I will also speak about state preparation today. So it sounds like a bit like the Magnus expansion. This is an overrepresented topic, like yesterday, but also you could argue it's important. So yeah, specifically, I'll be speaking about a heuristic method for preparing what I will call spin-coupled initial states, which we will use to initialize our quantum algorithms. And the claim is that this is very useful for simulating quantum chemistry in regimes where the electrons are strongly correlated. This is joint work with David Tu, Nicholas Lee, and Hugh Burton from Oxford. So the problem, which I'm sure you're all very familiar with, is the electronic structure problem. This is still, we do care about dynamics as well, but this is still a very central problem in quantum chemistry. And basically, it's just a huge eigenvalue problem where the Hamiltonian is the Born-Oppenheimer Hamiltonian. So we assume that the nuclei are clamped in fixed positions, and we just care about the many electron wave function. Typically, we care about the ground state and a bunch of the low-lying excited states. And as you know, the Hilbert space scales exponentially in the number of particles, and so brute force diagonalization of the matrix would be intractable. And if you think you have some clever tricks alternative to that, well, complexity theory tells you that at least the worst case instance of this problem is also QMA hard, so there's no efficient solution even on a perfect fault-tolerant quantum computer. Now, in practice, quantum chemists or computational chemists do solve this problem all the time, routinely, and sometimes very accurately and very efficiently. And this works because, I guess, intuitively, you would think that you have to search in this really big Hilbert space, but in practice, the intuition is that nature actually doesn't explore the full Hilbert space, and so the set of physically relevant states in let's say, molecules or materials is actually very, very small. It's a very small subset of the full Hilbert space. And so you can find good computational methods to approximate these states by essentially devising good heuristics. So typically, this involves identifying an initial state with a very simple description. So for example, a mean field state like Hartree-Fock, and then exploring the Hilbert space around it through methods like perturbation theory, coupled cluster. This is on classical computers, but you also do the same with phase estimation and VQE and any quantum algorithm. Although there are some nuances in how you explore the Hilbert space, but I won't go into that now. Okay, so the challenge with this is that a lot of the systems for which these kind of simple heuristics work very well, they're also solvable classically. So there's just no point of using a quantum device in those settings. And this is actually the argument for that reference in the bottom that you might have seen discussing the lack of evidence for exponential quantum advantage. It's not a super surprising argument, but it is something to really worry about if you're thinking about quantum advantage in this problem. And so what we will focus on in this talk is a heuristic for preparing initial states that's well suited for quantum computation in the sense that it goes beyond Hartree-Fock, but it's also hard, because you could argue if you find a good heuristic classically, then why don't you just solve the full problem, even if it's beyond Hartree-Fock. These states are highly entangled, and so doing things like coupled cluster or perturbation theory on top of them is actually, in general, very inefficient classically, although I'm not claiming any quantum advantage or anything like that. Yeah, so just to be clear, this should be obvious to everyone, but arguably, quantum algorithms for eigenvalue problems have this big issue that they depend very strongly on the initial state. You can say this very rigorously for phase estimation, where the probability of measuring your target eigenstate is directly proportional to, it's exactly the squared overlap between your initial state and whatever target eigenstate you're looking for, and therefore your number of runs is going to scale inverse proportionally to that squared overlap. In the case of heuristic quantum algorithms, there's no mathematically rigorous way of showing this relationship, but it should be intuitively obvious that if you start from a better state in, let's say, VQE, then you should be more likely to find your target eigenstate with, let's say, fewer gates. And if you're not fully convinced by that, then in this paper, we've done a bunch of numerics on that. Okay, so it's worth thinking a bit more carefully about what we mean by strong correlation in molecules. So the condensed matter physicists have a slightly different angle on this. This will be very focused on chemistry. So molecules, just a bunch of atoms, a bunch of electrons, no continuum of materials. So typical strongly correlated systems in chemistry are either bond breaking, so you just stretch a chemical bond, or transition metal clusters. So FEMOCO, which you've probably heard of, is an example of that. This big thing on the left here is like a sister of FEMOCO. Essentially, you have a lot of nearly degenerate orbitals and electrons that then couple through their spin angular momentum. And so mathematically, you can think of strong correlation in many different ways. There's no very clean definition. People are still arguing about that, and even in the classical community. But physically, in chemistry, it's very often the same phenomenon, where you have localization of electrons on subsets of the molecule. These electrons then partially fill some orbitals. So these are then called open shell orbitals. And the electrons then couple through their spin angular momentum. So this is what I mean by spin coupling. And it turns out that representing states like that requires expansion in the basis of Slater determinants that scales exponentially in the number of these strongly correlated electrons. So that's what makes it challenging to fit on let's say, a classical memory. And so obviously, in the context of quantum algorithms, we need some heuristics to approximate these states to initialize our quantum algorithms. Okay, so let me tell you a bit more specifically how we would go about the example of bond breaking. So let's take the example of N2. So this is just two nitrogen atoms. We're only considering the valence, so we have 6 electrons occupying 6 orbitals. This is in a minimal basis, but you could then use all of this in a larger basis as well. And what you see, this blue curve is just the Hartree-Fock energy as a function of the bond length. So the Hartree-Fock state is just the one that doubly occupies all the lowest energy orbitals. It's a very simple state. It's a product state in the computational basis. And you can see on the left, it's very accurate for the equilibrium geometry, where you have very weak correlations. And this is because the Hartree-Fock state encodes the point group symmetries of the molecule. So really, the many-body wave function is approximately a very delocalized object that's like all over the molecule. And the eigenstates of the Fock operator contain that point group symmetry of the molecule. And this is accurate at equilibrium. But as you stretch the bond, obviously, you're going to have some localization of electrons. So 3 electrons are going to go sit around the left atom and the other 3 on the right atom. And so Hartree-Fock just completely fails, and that's why you see this very bad energy. It turns out that if you look at the other extreme, this kind of strongly correlated regime, the state looks much more complicated. So in this case, it's a linear combination of 44 Slater determinants. But it's actually very predictable, because the reason why this strong correlation happens is just symmetry. You have symmetry between the left and right, and all the orbitals become degenerate. And so you can write down a state that correctly couples all the electrons and their spins in a very particular way. So in this case, it's ferromagnetically coupling the 3 electrons on each atom, and then antiferromagnetically coupling the electrons across the bond. And you can write a state like that without any computation. You just look up the Clebsch-Gordon coefficients for that particular coupling. And that turns out to be exact. And so the chemists call these objects configuration state functions. They're just symmetry-adapted linear combinations of determinants with a particular spin and spin projection quantum number and a particular intermediate coupling, like this ferromagnetic and antiferromagnetic that I just mentioned. But that's the key insight, is that this is actually very predictable from symmetry. And so I've told you about both extremes, kind of the weakly correlated and the strongly correlated. Of course, in the middle of this binding curve, there's going to be some transition between this. So it's a bit like in the Hubbard model where you crank up your U over T parameter. And basically, you can go about that by just building states that are a hybrid between these localized and delocalized states. And so I'm going to skip the details of how we construct these states, but the idea is that you can start from the Hartree-Fock and build states with an increasing number of strongly correlated electrons to approximate increasingly strongly correlated eigenstates. The issue with this is that, as I mentioned, the support of these states in the Slater determinant basis scales exponentially in the number of these strongly correlated electrons. And just if you combine these four states, you can build a wave function that's accurate across the entire binding curve. So it's this green curve here. And again, the nice thing is that these four states are all given by symmetry, and really the only thing you're variationally optimizing are these four coefficients, alpha, beta, gamma, delta, in the linear combination. And so I was speaking about energies, but you can also say the same things about the wave function. So in the case of Hartree-Fock, the blue line, has very poor overlap at dissociation, but if you use these spin-coupled states, then you get nearly unity overlap. And so in phase estimation, that would translate to a 16 times speedup. Of course, this is a problem that you can also solve classically, so it's not super meaningful in this context, but it kind of gives you an idea of where this can go. And of course, this is kind of a very bottom-up approach to building states rather than a very black box computational method. So there's a question of, okay, how often can you do this and for which systems? We've started exploring different systems. All these diatomics seem to be describable in this way as well. We've also looked at water, hydrogen clusters, and obviously now we're trying to extend it to more and more complicated systems. But I mean, my intuition at least is that it's going to generalize in this way. It's just how you go about finding these states is going to be more complicated the more complicated your system is. Okay, as I mentioned, these states are highly dense in the Slater determinant basis. But the nice thing is, again, just like how they arise from symmetry, they're highly symmetric and therefore can be mapped to very symmetric states. And in particular, in the quantum algorithms community, people have looked at these Dicke states, so that's a particular family of entangled states. They're the ones with all an even superposition of all the computational basis states with a particular Hamming weight. And it turns out you can map these spin-coupled states to something looking like Dicke states or linear combinations of tensor products of Dicke states, and therefore you can use the same state preparation circuits with some modifications. So effectively giving you efficient circuits with n squared number of gates and O(n) depth for preparing these states. So we avoid the state preparation bottleneck in that way. I think I'll just skip over this to not run out of time. Okay, so this is a bit. This is, I think, where this is going in the long term. So in the long term, obviously, we would like to solve systems, solve for the ground states and excited states of systems that are really intractable classically, which is not the case for the ones that I've shown you before. And again, classic example is FEMOCO. And there you can numerically see, and this was done in this exponential quantum advantage paper, that the overlap of a very simple state like Hartree-Fock or a particular configuration state function diminishes exponentially in the number of strongly correlated electrons, which again, after all I've told you earlier, shouldn't be a surprise. And you can there's some recent work by Pauline Olitrode and co-authors doing basis set optimization. So basically optimizing the orbitals given a configuration state function. And this gives you a slight improvement, but it's not fundamentally solving the problem of exponentially diminishing overlap. And so you might wonder, okay, what if we, instead of using Hartree-Fock or these spin-coupled states, why don't we just use whatever best classical method we have, like let's say full CI quantum Monte Carlo, and find this extremely highly entangled state classically, and then prepare it on a quantum device. The issue with that is, I mean, you might be able to find a state with like billions of determinants using full CI quantum Monte Carlo, but then you need to prepare that on a quantum circuit. And if you don't know any structure in the amplitudes, in the coefficients of your computational basis states, then you're just going to have to use a generic state preparation algorithm. And that's just going to scale with the number of states, the number of Slater determinants. And because the number of Slater determinants scales exponentially, and the number of electrons, that becomes very inefficient. And so this plot that I'm showing you here, this is not real data, so you have to take it with a grain of salt. But the idea is, if you were to assume that a state like the one I've showed you for bond breaking, that a state like that was accurate for describing the ground state of these iron-sulfur clusters, like FEMOCO, which is on the right with 34 of these strongly correlated electrons, then the state preparation cost of a black box state preparation algorithm would be very high, like over 10 to the 10 tofolis. And so in that case, it will be comparable to the cost of phase estimation with the current best methods, which in this case is qubitization. So obviously that will be a big problem for quantum algorithms in this context. Whereas instead, if you could find symmetry-derived states, like these spin-coupled states, the state preparation would be almost a negligible component. And you could translate this to first quantization. You could use the techniques that Bill was just talking about to map these states to a first quantized representation. I don't know exactly how that would scale with the number of determinants, but in principle, you can translate all of that to that setting. Yeah, you could also, instead of using a linear combination of determinants, think about running DMRG and preparing a matrix product state, which has a more efficient mapping because you have this tensor product structure that you can encode on a quantum circuit. There, the worry is, well, you might need very high bond dimension, and that might be inefficient classically, but also the state preparation. It's unclear. That's why I'm not showing any data on that. It's unclear what bond dimension you would need, but the state preparation could be comparable as well to like 10 to the 8 or something like that, depending on what accuracy you need. And it's hard to tell because we don't really know the ground state for these systems. There's some ideas by a team at Xanadu on taking a converged matrix product state with a very high bond dimension and then compressing it. I think that's interesting to look at, but it's unclear if it's going to translate to arbitrary systems. Okay, so just to conclude, I've claimed that to obtain quantum advantage in electronic structure, we need to focus on strongly correlated problems. And for that, we need good heuristics to approximate these states, either classically or quantumly. I've also claimed that this can be done by exploiting physical insight into the mechanism going on in these molecules and symmetries. And this is just leveraging the fact that eigenstates in nature are often highly symmetric, and they might look very complicated because their expansions might be exponentially scaling, but actually there's not that much information in them. And the spin coupling approach is one particular way of discovering these states and then parameterizing them on quantum devices. Also on classical devices, but like I said, taking advantage of that in classical algorithms is very difficult because it's hard to refine very, very entangled states. And like I said, their symmetric structure also allows very efficient quantum state preparation, which then is useful in quantum algorithms. And in the paper, we also did a bunch of numerics on VQE and subspace diagonalization, as well as adiabatic state preparation, to show that you really get some benefit in this case. Yeah, that's all. I think we have some time for questions.
We can do one questions.
Great talk. I have just from my understanding, is the idea sort of for your initial state preparation, you want to reduce it to a small number of CSFs?
Yeah.
So I can think of this as almost like a projection of like a CAST-CI calculation or something like that into a small number of CSFs and then going from there.
You could think of it that way.
Okay. Yeah, I just wanted to see what the difference was from a configuration interaction weight function to what you're doing.
So I mean, the difference is that these CSFs are a linear combination of a lot of determinants, and so and it's given by Eclipse-Gordon coefficients.
Yeah, thank
There's
you.
a lot of structure in the state. Yeah.
Let's thank the speaker.